we'll probably need to wait another 5 to 10 minutes because so far we have only 5 students in this Zoom session. So let's wait for another 5 to 10 minutes, okay?
Okay.
Okay, Prof. Okay.
Okay, so I think probably we can start now. Assalamualaikum and good evening, everybody. I'm going to show about the lighting of this room tonight. But I'm going to share with you the slides that I have already uploaded that to our Travelers. Can you all hear me? Yes? Good volume? Okay. Right. So we are going to continue our discussion today to quite an important topic, fundamental topic or fundamental section in digital image processing. Last week last 2 weeks we have discussed about the formation of image sighting based on reflectance and illumination. So today what we are going to discuss is about how an image been formed in the context of the image projection. Yeah? It's a propagation of lights to the sensors in the camera. So there are a few assumptions in digital image processing. If you use Adobe Photoshop or if you use any image processing or graphics design software, there are a lot of algorithms as simple as increasing the brightness, increasing the saturation, or make it sharper, make it more blur, and etc. So those kinds of image processing can only be done if we have some assumptions about how the image are being created. Okay, so number one, what is important is we talk about linearity, yeah, of an image. Oops, okay. Right. So we talk about the linearity of an image. So in other words, when we talk about digital image processing, we are talking about processing them in a linear function. Okay. So what linear means? If you look into this simple equation, if H here is an operator, H is an influencer, a factor that change the quality of the image. Yeah. If H here is changing the whole quality of the output image, AF plus BG, whereby F and G are images. Yeah, F and G are images. A and B are simple scalar or multiplier. Yeah. So we can call the image formation function, or we can assume them as linear if we can separate the two terms of AF and BG. So instead of having one term here as an output image, we can separate them into two individual images. Okay, so if I may give you some analogy, the first part here, let me change color. The first part here, okay, the first part here is actually just one image. Okay, we can call this as an output image. Okay, so an image is considered as linear if one output image, it can be separated into two terms. One is this image and another one is this image. So in other words, we can say that an output image here is equivalent to some operation of the first image plus the second image. Yeah? So one output image can be split into multiple images, and if I want to describe from left side of the mathematical expression to the right side of the mathematical expression. If I want to do vice versa, we can say that if you have multiple single images, you have many single images, many individual images, if you add them together, it will be equal to the output images on the left side. So this is what we call as linearity in an image. Yeah? If we want to talk about the non-linearity of image, meaning that for non-linearity, meaning that this is cannot be separated into individual images. Okay, as simple as that. Yeah. So in our discussion throughout this semester, this is one of the assumption. Yeah. In fact, a very important assumption that we need to make. Only then we can proceed with all the algorithms, methods in image processing. Yeah. So this is one very important assumption, that the image that we are dealing with in our digital image processing class for this semester are all linear image. Non-linear image processing is actually a very big topic by its own. Yeah, non-linear image processing. You can also Google that. There are lots of non-linear methods in image processing. Yeah, I'm not saying that it cannot be done or it cannot be solved, but there are totally different ways of doing it. The majority of methods that we have in the market, in the graphic software, yeah, if you have Adobe Photoshop, PaintShop Pro, Dreamweaver, and all the graphic designs software are all based on the assumption that image formation function we have is based on linear images. Okay, so that's one. Number two, we can also say that the factor I mentioned earlier, okay, the factor that I mentioned earlier, which is H, yeah, this particular factor, it can either be a good factor, yeah, meaning that some factors that will improve the quality of the image. Yeah? So this H can either be a good factor, yeah, plus points, whereby with this H, for example, we can see the image clearly, or it can be a bad factor or a negative factor whereby it will make the image becomes more blur, yeah, or less sharp. So that H, that particular H, we call that as a point spread function. Yeah, as a point spread function. So why we call that as a point spread function? Yeah, because the best and ideal situation is if at the source level you have a point, yeah, and at the detector you can detect that as 1 point. Yeah, so we discussed last time that the image has two components. One is the illumination and one is the reflectance. So imagine that you have a source of light coming from sun, for example, and it will be reflected through a canvas, and the size of of this particular object, if we can remain that as the same size, that would be the ideal case. But in most of the cases, the size of the image, when it is been recorded in the output image, or in our camera, it will be recorded as having a slightly bigger size. Yeah. So if I draw a cross-section profile, if we have a cross-section profile from here to here, from left to right, if I draw a cross-section profile, if we have this profile as our image object, at the output image, we may have a slightly wider image profile from left to right. Yeah. So what I mean by image profile is the profile if I draw from left side to the right side. Yeah, and if I take that profile. So this particular scenario of having a bigger blob at the output canvas is a scenario of spreading the source from a point. So that's why we call that as a point spread function. Okay, so this is in one case of looking an object as a very tiny object, therefore it will reflect a point. What if we are looking at a big object, yeah, a big object. So in image processing, we are assuming that every point here, yeah, every point here, it will be reflected and it will be recorded in the output canvas. Therefore, we are saying that if you have an extended object size, meaning bigger than 1 point, then the assumption here is the image object that we record at the output image is made up from many points. We have lots of points here. So it made up from many points from the original object. So that's why we still call that as a point spread function. So this particular operator of H, which is now we call that as a point spread function, PSF in short, yeah, it relies on the original position X and Y and the relative position alpha and beta. Okay, what is X and Y and what is alpha and beta? Let's go next. Oops. Okay. All right. So okay. So that particular point spread function H, okay. Well, I'm going to use a small h from now onwards because I want to differentiate between h in spatial resolution and h in frequency domain, which we are going to see that later. Yeah. So we are going to use a small h, not the big h as in the previous slides, but it relies on the input value at the position of x and y input and the output value at the position of alpha and beta. So what is X and Y and what is alpha and beta? If you have an original object just now I mentioned, and then you have the object that is being recorded. And this is the original object. For example, you saw a car. So the car is the original object. You take a picture of the car using your mobile phone. So the picture that you took is the output image here on the right side. Yeah. Now, so in other words, this is we call as input, yeah, or object, and this is the output. Okay, so now this, imagine this particular object, we still have a canvas to represent the Cartesian coordinates. We discussed about that 2 weeks ago. Yeah. So if we have a canvas, so that we can represent that in a Cartesian coordinate, then we can have a value of x and y. Yeah. So the same concept in output image, but now instead of using x and y, we are using alpha and beta. Okay. So why I'm using alpha, beta, and not x and y in output image? So that we can differentiate between the input and the output. So now imagine this particular point here I mentioned in the previous slides, as if that it is actually been propagated to the output image. And that's the reason why we can represent the point spread function as a relative value of x minus alpha to show if there is any difference between the input and output. Yeah, if the input and output is exactly the same, then h minus alpha will become 0. So similar to y minus beta, because it's going to show whether there's a difference in terms of the original location in the input image and the location that is being recorded, yeah, alpha and beta. Okay, right. Next, okay, there are lots of mathematics today. Okay, don't feel sleepy, yeah. Don't go to sleep yet, yeah. So now, this particular H that relies on input at location of x and y and output at the location of alpha and beta can be simplified to become x minus alpha and y minus beta. And if we have a delta, yeah, a delta, meaning that if we just have a point, yeah, just have one point, the whole terms can be then simplified to become one, yeah, because it's a delta, yeah. And well, if we forget about delta first, and if we just plug in this particular equation into the whole process I mentioned just now, if fxy is the input image, yeah, fxy is the input image. You mentioned, imagine just now I said that we have input image, it projects become the output image. Yeah, this is input, this is output. Yeah, we might have one point here, and in the output you might have a blob, a blob. So this input image, we call that as fxy. Yeah, fxy. The factor that contributes to the degradation process is called as hx alpha y beta. Yeah. Then if we run the whole process for the total size of the image, yeah, from x0 to n minus 1, from y0 to m minus 1, then we can get the output image, and we can call the output image here is as g alpha beta. Okay. So these particular two summations here, is a process of what I mentioned earlier, that at the output image, the way that we want to or the way that we create the output image is by looking at many point sources, yeah, and then we sum all of them over the total size of the image. So this is the image formation function that is important for you to remember and understand. So this hx alpha y beta is a function. Therefore, this particular elements here, it can be represented by, for example, x plus y alpha plus beta. Yeah. So if this is the function that we have from our experiments and etc., then you can actually reduce the image formation function. It becomes now summation of f xy, and then we can have h with the expression here. Okay, Next, we can also, okay, hold on a minute. Not sure why it doesn't change. Okay. Next, we can also try to further simplify the equation, yeah, instead of just using instead of just using x alpha beta, we can also use this particular relative positions of x, y, alpha and beta, and we can plug that into this equation, and now it becomes f xy. This is the same. This is the input image. Yeah, and we can say that the point spread function now becomes x minus alpha and y minus beta. Okay, so this particular form of equation is a very popular equation, which is showing that an output image can be created by doing a convolution, yeah, f, yeah, a convolution with h. Okay, so the whole term here on the screen here, fxy, hx minus alpha, y minus beta, is actually a popular form of a convolution. Yeah. And here I'm using this particular symbol to represent the convolution. In other words, we can further simplify this equation by saying that G alpha beta is a product of x fxy convolve with h. You can either put that as x alpha y beta, or you can just say that this is a convolve with alpha beta. Okay, so this is what eventually we are going to use, yeah, because this particular convolution can further be simplified. You see, we started from a general theory of image propagation and etc. And at the end, this particular equation that you saw just now can be further simplified if we use a frequency domain by saying that G, okay, mu nu, is actually a product of f mu nu multiplied by h mu nu in frequency domain. So I'm not sure how many of you well versed about convolution, yeah, but it is much easier to process image in frequency domain. This is in frequency domain, yeah, in frequency domain, as compared to the spatial domain, yeah, the spatial domain, because we are only going to deal with multiplication rather than convolution. Okay, I'm not sure about background. Some of you, if you are unable to follow me and you don't understand about the frequency domain and etc., you need to let me know. Okay, because I think last time some of you are from maybe computer science, maybe science, yeah, maybe not from engineering. Those from electronics engineering or electrical or computer engineering, I think you have heard about frequency domain. But if you are not familiar with this, you let me know, because I do not know, to what basic level that I need to teach you. Because maybe you have lots of varieties in terms of background of your first degree. Okay, now in image processing, most of the time we want to improve the quality of the image. So when I say the quality of the image, meaning that the output image that you receive, this is the output, the quality is bad. Yeah, the quality is bad. So what you want to do now is that the only thing you have is the output image. How you want to improve the quality of the image? Basically, there are two general methods. One is called image enhancement and one is called image restoration. Okay, what image enhancement means? Image enhancement means that similar, you take picture using your mobile phone, you get not good image. So you try to improve the quality of the image without trying to understand about, how the image been degraded. Yeah. So you do not need to understand this. You have the output image and you want to try to get or to improve the quality of the image, meaning that you want to try to get to the original or close to the original image. So that is the case of image enhancement. Meaning that in image enhancement, you just get the output image and you want to try to get as close as the input image. Okay? Remember, this particular H function I mentioned earlier, it has a good effect and bad effect. But most of the time, it has a bad effect. Yeah, it has a bad effect. Therefore, because the convolution or because of the multiplication in this particular form, and the simplified form is a convolution, because a convolution between F and H. F is the input image. This is the best image, the original image. The input image is the original image. The original image has been convolved with the input image is being convolved with, the input image is being convolved with the point spread function. And because of this point spread function has degraded the input image, then we get not a good output image. So the whole purpose of image enhancement is trying to improve the quality of the output image, improve the quality of G, so that you can get that as close as possible to F. So that is the case of image enhancement. We have a topic, one chapter on that later. Another category of in this case, we are trying to improve the quality of the image is by improving the quality of the output image using the approximate value of H. Yeah. So you try to get, you have the output image and then you try to determine what is the point spread function, and then you will use both information to try to get to input image. Okay. So why you can, or how you can do that? Okay, I did mention that in frequency domain, we have G mu nu equivalent to F mu nu multiplied by H mu nu. If we know G and H, we can calculate F mu nu equivalent to G mu nu over H mu nu. Yeah, we can do simple mathematics. Yeah. We will go into the process when we go into restoration chapter. Okay, so next. Okay. Yes.
I have question. So basically, PSF value is a noise or variable value that we introduce in our image to improve our image or what?
No, we have not yet got into, or we have not yet arrived into noise. We will have that in, I think, a couple of slides. Oh yeah. We're going. I'm going to explain to you about noise later. This is not yet noise. This is just one point being spreaded into a block. Yeah, and most of the time, this contribute a lot to your blurry images, not to your noisy images. When we mention about degradation, meaning when we mention about degradation, degradation meaning why the image becomes so low quality in digital images. This is due to number one, point spread function. Yeah, meaning that we have a very bad point spread function. Yeah. If we have a very good point spread function, then the image will not be degraded. The quality of the image will be good. The second factor of having bad image is noise. Okay, so the ones I mentioned earlier when we discussed about the point spread function, these are all referred to H. Yeah, small h in spatial domain or capital H in frequency domain. Noise, we are going to use N for that in spatial domain and capital N in frequency domain. So we have not yet discussed about this. We will have a slide after this on noise. Okay, so far we discuss about point spread function only. So this contributes to most of the time why your image gets blurred. Okay, any other questions? All right. Okay, if not, I mentioned just now that if I use G equivalent to F multiplied by H, okay, we can easily get to the original very good image of F. If we do a simple algebra rearrangement by dividing G with H, we have G, of course, because G is the output image, but we do not have H. So how to extract H information in our image? Yeah. So in research, we can actually do that by either trying to get directly from the point spread function. What I mean by directly from the point spread function, we can simulate a point, yeah, one point, a very small point, yeah, and maybe I use 1 millimeter for the diameter of the point, and then if you take picture in your camera, okay, then we can measure the diameter of the image in the camera. Maybe now it becomes 2 millimeter. So you see, originally it's 1 millimeter. Once you capture that in the camera, it becomes 2 millimeter. So there's a factor of blurry there because of the point spread function. So this is one. Okay. Number two, we can also, instead of using a point as our source, when I say source here, meaning that you can have like a torchlight. You can have a torchlight and then you can create a cardboard and put just one hole, small hole with the size of 1 millimeter. Okay, so this is one experiment that can be done. That's why I use this title, experimental data for point spread function. This is how an experiment can be done to see the effect of point spread function, yeah, to your blurred image. Second way of doing that is instead of having a point, which sometimes can be very difficult to ensure you have a very good round shape, yeah. So instead of doing that, what we can also do is, if you have two papers, yeah, if you have two papers and then you put torchlight, and then you capture at the image, you will get one line, yeah, of lights. Yeah, you get one line, because you have two papers. Instead of having to poke one hole, round shape hole, which is, you cannot determine whether it's really round shape or not. You just use two cardboards, project a torchlight, and then you can get a line of lights. So what you can do is you calculate, or taking a profile from here until here. Yeah, if you take a profile, so you take a profile, you get something like that. Yeah, for one angle, and then you assume that, say that the diameter here is A, or we call it as a full width half maximum, diameter lah, to make it easy for you. If the diameter is A, we now assume that this particular diameter A, is, this particular diameter A is actually the same diameter for that particular point if we rotate that over 360 degrees. So at the end, you have a blob with the diameter of A. Okay, so that's how we can try to get values for H. So if you have values for H and you have G, therefore you can try to restore what is F. Yeah, or sometimes if you read from books, they use F hat, which means that we try to get as close as the original F, as close as the original input image, right? So the whole discussion that so far we had this evening is all about point spread function. But in an image, apart from point spread function, most of the time we also need to deal with noise. Yeah, with noise. If I want to plug the noise term in our image formation function, how is it going to be looks like? So we have G, okay. We have G just now, G alpha beta, equivalent to summation, meaning it will add all points related to the output image. Both summation in X and Y, this is X, this is Y, both summation in X and Y for F, X, Y, and H, X minus X minus alpha, Y minus beta. So this is the original image formation function in spatial domain. Okay. Spatial domain means the real space that we are living on Earth. Yeah. Real domain, spatial domain, or sometimes they call it as a real domain. Okay. So in this particular original image formation function, there is no noise term. Yeah. So we only discuss about a point from the input image is being spreaded. Yeah. But as I mentioned, the degradation process of an image is due to number one, point spread function, and number two, noise. How can we add the noise term in this image formation function? It will really depends on the type of noise here. Yeah, the type of noise. The easiest type of noise that normally we consider is called an additive uncorrelated noise. Yeah. So what additive means that the whole function here, we just add a noise term. And what is uncorrelated means that it has its own value. It has its own value. So this is called additive noise because you add, and uncorrelated because it has its own value. Okay, how's other types of noise may looks like? Okay, we may also have a multiplication noise. Multiplication, a dot multiplication, or we may have a divisive noise, or we may have a deductive noise, but in our assumption for this digital image processing, we always consider noise as additive noise. So now, okay, that is additive, multiplication, division, and etc. What it means by correlated noise? Okay, so let's maintain this as additive noise. So correlated noise means that the noise is depends and not independent from either full width from either the input image or the point spread function. It could be something like n f x f y. It could be something like this. Now you can see that we have a f term, that this particular term is actually this term. Meaning that the noise depends on the input image. So this is what we call as a correlated noise, which is more difficult to solve this particular problems. And that's why the assumption that we use in our image processing class, number one, the assumption the image is linear. Number two, that if you have noise, the noise is considered as a additive uncorrelated noise. Okay, so uncorrelated means that whatever happened in the input image, it is independent from the noise. Okay, when you say this is additive, meaning that if in one image you have a point here, maybe, okay, let's use pixel as an example. Okay, I have taught you that we could have pixels, and say that this is 3 bits image. 3 bits means that you have value of 0 until 7. So let's say that this is 0, 1, 2, 7, 7, 0, 1, 2, 1, 1, 3, 1, 7, 7, 7, 7. Okay, and noise. Okay, let me give another example, easier one. Okay, let's say that I only have a 2x2 image, easier one. Okay, 2x2 image of 3 bits color. So say that I have 0, 1, 7, 6. Okay, this image is this particular, this image comes from the whole term here, becomes this image. Okay, and then noise. Okay, we may have like 0, 1, 1, 1. You see, because it's independent. It's independent from the left side. And this particular noise term comes from here. So since that this is an addition, therefore the output image that you'll get is 7 plus 0, 7, 6 plus 1, 7, 0 plus 1, 1, 1 plus 1, 2. So this is the output image after it has been corrupted by noise. Okay. So generally, I just would like to recap that in our digital image processing class, we need to assume number one, the image is linear. And number two, the noise term is additive uncorrelated noise. Okay, sorry for my on-screen bad handwriting. Any questions? Oh, already close to 1 hour. Any questions?
Prof, how can we predict this correlated noise? Is there any way to predict?
How can we predict the noise? Is that what you're asking?
Correlated noise.
How we can predict correlated noise?
Yeah.
No, we cannot predict correlated noise.
Means
That's why
if
when that's why what I'm trying to explain from the beginning is, if you have one image, yeah, and this image we label that as the output image, yeah, so it is a G alpha beta. You have the output image, yeah. You do not know whether this image comes from correlated or uncorrelated, and you do not know whether it is additive, subtractive, multiplicative, or etc. You do not know. That's why we assume, yeah, that number one, the image is linear, meaning this particular image, it can be split into multiple images. It comes from multiple images. That's one. Number two, if the image has been distorted by noise, we assume that the noise is an additive noise and uncorrelated noise. We assume, yeah?
yeah.
So, can you assume that this image is correlated? You can. But if you assume the image is correlated, you cannot use the techniques that we are going to discuss in this particular class. The ones that in the textbook, digital image processing textbook, are all based on the assumption that the image is uncorrelated additive noise. Okay, that's why I use the word assumption. So we assume that the image is additive, uncorrelated additive noise. If you want to assume that the image is correlated, then you cannot use the techniques that we are going to discuss in this in this class. But it has been proven. It has been proven with all the techniques that are presented in the textbook and in this class that in most cases, if you have a bad output image, in most cases, it is adequate for you to assume you have uncorrelated additive noise. It is sufficient. Even with the techniques that we have, uncorrelated additive noise, you can improve the image, the quality of the image. So it is sufficient to just use that particular assumption in our class.
Thank you.
Okay, any questions? Okay, if not, then can you give me like maybe 5 minutes, okay? Let me drink some water and I come back because we are going to go to the next slide. Okay, so we finished the second slides and we are going to go to the where is it? The third slides. Yeah. Okay, so we are going to the first category, which is called as image enhancement. Okay, give me 5 minutes. Okay, take a break. Okay, can we continue? Are you still there? Sleeping already?
Yes,
Not
Prof.
yet.
No, Prof, we are still here.
Ready. We are ready.
Okay, good. So now we are going to the first category of improving the quality of the image using a technique of image enhancement. Okay. As I have shown you in the previous slides, generally, when we want to say that we want to improve the quality of the image, there are always two categories. One is image enhancement, and one as image restoration. Yeah. So image enhancement, first of all, it can be performed at either spatial domain or frequency domain. Yeah. Or sometimes we have also other available domains. Yeah, like for example, wavelet domains, yeah, and etc. Yeah. Okay, before I go further, can I just make sure that all of you have heard and understand about frequency domain? Anybody don't understand about frequency domain? Okay, so no response, meaning everybody understand, yeah? Okay. Okay, do you all understand about spatial domain? What it means by spatial domain? Anybody don't understand about the word spatial or spatial domain? Okay, so no response. I believe everybody understand. If you understand, say yes.
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 Yes,
Just two voices, three voices. So the rest, are you
Yes, Prof.
okay? So everybody understand, yeah? Because I mean, don't be shy. If you don't understand, let me know, because I can explain further. Otherwise, if you all know already what is spatial domain and what is frequency domain, then I can just go ahead with the rest of the explanation about image enhancement. Okay, so all of you understand, yeah, about spatial domain and frequency domain? Yes. Okay.
Yes, bro.
All right. So as I said, if you don't understand, you need to let me know. Okay. Otherwise, I'll just go to the next point. Okay. Coming back to image enhancement, it can either be performed at spatial domain or frequency domain. Yeah. But the easiest way, maybe for us to understand, is if we perform that in spatial domain. Yeah. Because spatial domain means that you can see the pixels. This is spatial domain. Yeah. I mentioned earlier that we call that as a real domain as well, because in this real world, normally we divide the domain into time domain and spatial domain. Time domain is whatever signal that the X value here is time in second or minutes or hours. Yeah, like for example, my voice. I'm teaching all of you in 2 hours time. Yeah, so that is time domain. Spatial domain means things that you can see, because we have X and Y, and the X and Y are representing the pixels, and you can see the pixels as a form of an image. So that's why we call that as a spatial domain or real domain. Okay, coming back to here. Why cannot clear? Hold on a minute. Not sure why suddenly I cannot clear the screen. Okay. Anyway, the easiest way of doing image enhancement is in spatial domain, because you can see what's the effect of the image enhancement algorithm. Yeah, and the easiest way of performing image enhancement is by putting an operator to the image. Yeah, and the operator is called as a transformation factor, or T. Yeah. So meaning that if you have any image, it can be F, it can be Z. Yeah. So just not to make you all confused with the previous slides. Yeah. Okay. Just not to make you confused with the previous slides. I mentioned that you have an output image of G alpha beta. Yeah, G alpha beta. That's your output image. So now imagine that you put an operator to that. You put an operator to the image that you receive, then you will get something that is, maybe I put this as G hat alpha beta. If you want to relate this particular slides with the slides I mentioned, I taught you earlier. Yeah. The whole purpose here is by putting one transformation factor of the output image, you should be getting a better image. Okay, let's look an example. Oops. Okay, so this is an example. Okay, yeah. Oh, sorry. Before going into example, that particular transformation factor, it can either give effect to one individual pixel. Yeah. So if it give effects to only one individual pixel, we call it as a pixel processing. If it give effects to a group of pixel, yeah, a group of pixel, we call that as a group processing. So let's look at an example of a simple transformation factor that we have. Okay. Imagine that if you have a 3-bit image, yeah, and 3-bit image meaning the color runs from 0 to 2 to the power of 3 minus 1, meaning the color 0 black. You have 1, 2, 3, 4, 5, 6 until 7 white. So now imagine that we have black here, 0, 1, 2, 3, 4, 5, 6, 7. 7 is white. Yeah. And you have 0, 1, 2, 3, 4, 5, 6, 7. Okay, 7 is white. If we have one input image, say one input image, yeah, with this particular same bit depth, one input image with size of 2 by 2 spatial resolution and 3 bits color resolution. So say that this is 0, 1, 7, 5. Okay, this is the input image. Yeah, this sorry. Okay, again, just not to make you all confused with the previous slide, I'm going to call this as the image. Why I cannot? Okay, I'm going to call this as the image that you want to improve. Yeah. So this is G alpha beta. This is the image that you want to improve. This is the image that you capture in the camera and you want to improve. Okay. So this is the image that you want to improve and you want to get one output image. And the size is similar, it's 2 by 2. Now, if my transformation function is a simple linear like this, okay, and I do an interpolation, yes, 0, it becomes 0, so 0 becomes 0. 1, I interpolate 1, yeah, okay, 1, you get 1. I interpolate 7 from R to S, yeah, because this is the one that I mentioned in the previous slide. Yeah, you have T, G alpha beta, yeah. So this particular R is G alpha beta, which is on the y-axis. So 7 becomes 7, and if I interpolate 5, becomes 5. Okay. So this is going to be our output image after image enhancement. But as you can see here, there is no change at all because we are using a linear function here. Yeah, linear function. Any questions? Okay, if there is no question, okay, let me try to clear first. Okay, I wonder why it doesn't clear all of that. Okay, anyway, right. So that is our output image. Yeah, if we are using a linear function. So this is G alpha beta. So now, if my transformation function is not a linear like that, but rather it is actually exponential like this. Okay, then my input image from 0, maybe you still get 0, but 1, if I interpolate, maybe you still get 0. Okay, 7, 7, if I interpolate, maybe you still get 7, but 5 here, if I interpolate, you get 1. So this is a pixel point processing whereby we change one value of the pixel at one particular time. And you can see based on this operation of image enhancement, the quality of the image now is changed. Yeah, whether it's improved or not, that really depends on the application. Some application require more brighter image. Some application require darker image. Any questions? Okay, if not, then now imagine that you have a step function. 0, 1, 2, then you have a step function. Until 6, then you have a step function. Yeah. So anything with 0, you get 0. 1, you get 0. 5, you get 3. And 7, you get 7. Yeah. So this is going to be the output image. So your role here is to find what is the best transformation function. So do I have an answer to that? No, because it really depends on your application and what are the issues that you want to solve. Yeah. If your image is too dark, yeah, if your image is too dark, yeah, maybe you would like to, okay, if your image is too dark, yeah, dark means that you maybe your image all from 0 until 3 only. Yeah. If your image is too dark, okay, say that this is your input image, you have 0, 0, 1, 1. Okay. If your image is too dark, then the way to improve it is by using this particular equation. Oops. This particular equation. Because anything with 0 will maintain as 0 and anything with 1 will give you 7. So you have a good stretch. Otherwise, earlier your image is 0, 0, 1, 1. It is very dark, and even it's actually quite difficult to differentiate between black and very dark gray 1. But now if you have this particular function, you can change the image and it becomes 0 and 7. So now you have a very good contrast of an image. Yeah. And I introduced the word contrast just now. What contrast means that in one image, what is the range of maximum minus minimum? The higher the range, the higher the contrast. So in this case, the contrast is 7 minus 0 equivalent to 7. If I have my earlier example, 0, 0, 1, 1, then the contrast is only 1. So this is not good. This is good. Yeah. So that's why the question that I posed to you just now, what is the best transformation function? So there is no answer to that. It really depends on your application. Yeah, which application or which image that you want to use and what are the problems that you are facing. And based on that, you need to create and find the best transformation function so that you can impose that on the input image and you get a better output image. Any questions?
Prof,
Sorry?
Yeah, bro. I think if we use this transform function to change a picture to another picture, maybe the quality of picture will be reduced.
The quality of the image, you know, it's like there's a saying, beauty is in the eyes of the beholder, right? It's a popular saying, beauty is in the eyes of the beholder. So when you see an image, you must identify what is the problem with the image. Is it too blur? Is it too noisy? Is it too dark? Is it too bright? So this particular image enhancement, this is a simple image enhancement technique, but this image enhancement will only work if you identify what's the problem and you try to find the best function. You know, when I say function, I'm referring to here. What is the best function in here? It could be, you know, this simple graph, or it could be something like exponential, reverse exponential, yeah, or it could be like a step function I mentioned just now, yeah, or it could be something like this. Yeah, it could that there are a lot of functions that you can put in the transformation function, but which function is the best? It depends on what is the problem that you want to solve. Yeah? And people have been publishing papers about this particular function for a specific application. So if you currently have a specific application and you want to improve the quality of the image, you try to get what is the best transformation function. If you get that and you can see that the quality of the image is improving, then you can actually publish a paper on that. Yeah?
Yeah.
Any other questions? All right. If not, I'm going next.
Sorry, Prof.
Yep.
If we have some effect on the axis of the, for example, if we are modeling a point source, but in the output image we have some effect on the just on the axial side, on the x-axis and on the y-axis, then what probably the transfer function will be more suitable to model this problem?
Well, I don't have answer to that. Because you know we need to try to find what's the function, and we need to do the pixel processing and get the image and see the image. Without seeing the image, we do not know whether the image becomes, you know, better or worse.
Right.
Okay.
Right.
Any other questions? All right, so if not, then let's go next. All right, so another, sample, a few examples of image enhancement that are quite popular is, for example, image negative. Image negative means that, you know, for image negative, say that you have an image of 0, 0, 1, 1. You want to make a negative value of that. Yeah, make a negative value of that. Then you have function like this. Yeah, 0 until 7, 0 until 7. Whereby now 0, it will be interpolated and become 7, 7, 7. And 1 here, if you interpolate, it becomes 6, 6. So now you are like doing a image negative. So that's how people do image negative in all the graphic software. Yeah, they just use this particular function. Whatever that you have in the image, it will be interpolated and it will be changed to the inversion values or inverted values, yeah, of the function. Okay, we can also have a log transformation. Yeah, a log transformation with a multiplication of C. Yeah, we have some log function. Yeah, or we can have a power law transformation. Yeah, power law transformation. I think it is like this, if not mistaken. Yeah. So we can have lots of functions to be applied on image enhancement, but it depends on what are the applications for. For example, in power law transformation, it depends on value of C and gamma. So you can have like something like this, this. It is being used as a gamma correction for your monitor. Yeah. In your monitor, if you see that as yellow, yeah, this is yellow, right? This is yellow. You really want to see the original value of yellow. But because of the imperfection of the materials in our LCD and previously in our CRT monitor, sometimes the value in the pixel is yellow, but the value that is being displayed is a different type of yellow. So that's why we need to use these input values to do correction from the input to the output, to the one being displayed from your or in your monitor. Okay, so that's what we call as a gamma correction. So that's why in the previous question, I mentioned there is no one function to say that this is the best function. We need to know what's the application, and after that we need to view that, because image enhancement is very subjective. It depends on you to say whether the image is better or worse. Okay.
Dr. Question.
Sorry. Yes.
Question. Is there any guidance or rule of thumb in determining values of coefficient to be tried out when we process our image?
Okay, to start with, normally we use try and error. So meaning that you just plug in any values first and you see what's the result. Yeah, that is a normal starting action by any researchers. Yeah. However, if you know specifically what's the problem, like for example, your problem is the image is too dark. I mentioned earlier just now. The image is too dark, and you want to improve the contrast. Then you shall know that if the image is too dark, then you need to have something like this to improve the quality of the image. And this particular value here is actually the maximum value that you have in your degraded image. Okay, so there is no rule of thumb. It really depends on the image itself. So meaning that this is not very adaptive. Well, this is a very simple method anyway. So this is not adaptive. This is very static. It depends on the image itself. You see the image, what you want to improve, then you try different functions, or maybe you can Google and try to see from the literature review for that particular problem, what are the functions that are suitable for that. And you try to plug in and see whether the image is improving or not. Okay.
Okay, doctor, thank you.
Right. Okay, next. Okay. Other than that, we have also, more difficult or more functions. Yeah. Like for example, we have a piecewise. In this, the purpose is to stretch further contrast. We have gray level slicing. Yeah, we have bit plane slicing. Yeah, these are many. These are some of the functions available and has been published by researchers. Yeah, for that particular transformation function. Yeah, but I'm not going to go to that in a very detail. The whole idea here is for all of you to understand that the original concept is simple. You just need to know what is the right function for your specific problem. If your problem is about the contrast, meaning the image, you're not able to see the details, yeah, the contrast is low, then, for example, piecewise linear, yeah, could be the best method. Piecewise linear is the method I mentioned just now, yeah, whereby you have a certain area linear and certain area is just a plateau. Okay, and okay, next, in image enhancement, okay, we discussed first just now using transformation function. Okay, now first, okay. Just now we use transformation function of G alpha beta. Okay, so finished with this already. I'm now moving to the second technique, basic technique, in image enhancement, where this technique is called as histogram processing. Okay, histogram processing. First of all, you need to understand what histogram means. Okay? Histogram, if I want to explain that in words, it means the frequency of the bits or the color appears in the image, and the frequency, how many times. Yeah. For example, if you have a 2x2 image, 0, 0, 0, 0. If I want to plot histogram 0 until 7, this is the gray value. The y-axis here is the frequency, or we can also call that as a probability of that particular color to appear. That's why in the textbook they call that as P. Yeah, P means the probability of that particular color to appear. Yeah. So in this case, 4, we have 1, 2, 3, 4. So histogram in this case is just one plot here. Okay, so let's look at another example. Say that now I have 0, 0, 1, 1. Yeah, so 0 appears 2 times. Okay, hold on a minute. Okay, 0 appear 2 times, and 1 appear 2 times. So this is your histogram. Okay. Any question about histogram? All of you understand what histogram means? Okay. Frequency, or how many times 0 occurred and 1 occurred, you add the frequency, you get the total number of pixels. And this particular example, we just have 2 by 2 pixels, meaning you have 4 pixels only. Imagine we have a lot of pixels, yeah, so you'll have a lot of frequency, yeah, so you have a very good distribution. So for that particular, and refer to the graph below here. This is just a general function. If you have a first dark, second low contrast image, how's the function looks like? Yeah. So first of all, if this is, we know that this is actually going to be 0, and this is going to be the maximum or white, yeah, maximum color. Yeah, 0 and white. Yeah, and say that this is in the middle. This is in the middle. We can see that most of the pixels lies in the darker region of the image, and that's why we call it as a dark image. Many pixels appear in the darker region. Yeah, 0 black, and then dark gray, dark gray, dark gray. Yeah? And here is middle gray. Oops, here is middle gray, but we don't have many pixels after middle gray. That's number one. Number two, we say that this is a low contrast because most of the pixels are residing here, and therefore we are unable to see a good stretch of the image. On the other hand, we can see here that most of the pixels are residing at the very bright region. That's why we call this as a light contrast. Yeah. So, in other words, if I may summarize, if we have a lot of contrast in the darker region, then your histogram will be look like this, meaning that higher frequency in the lower value. If you have something like this, meaning that you are going to get a very bright image. Okay. Low contrast means I mentioned maximum minus minimum. So that if you suddenly get things in the middle only like this, then if you get the range here from maximum to minimum, and the range does not cover the whole stretch of the y-axis, then we call that as a low contrast. High contrast means that you have a good spread of image or color throughout the the x-axis. That is considered as high contrast. So we can use this particular information of histogram to further improve our image. Okay. Oops. Okay, why is it not? Okay, right? So, oops. So this is an example. You can see here that this is a dark image because all the value of the pixels, they lie in the dark region, whereby in this in the bottom image you can see that the image is too bright, and therefore all pixels appear in the brightest side of the histogram. Okay, so that's why I mentioned earlier, you need to look at the image first, and then from there you shall know what would be the transformation function if you use the previous method. Yeah? But for this method, the whole idea here is, imagine if this particular histogram here, it can be stretched out. That's your purpose. If you can stretch out this particular histogram, and eventually you get something like this, and you stretch out, then the image will become better. So that particular technique is called as image equalization. Okay, we go next. Oops, why doesn't one? Okay. So that particular technique is called as histogram equalization. So to do histogram equalization, you need to first understand about histogram. Okay. I mentioned that we use P. Oops. Okay, we use P because it shows the probability of the color to appear. Yeah, and when we express probability, yeah, normally we are going to use total probability has to be equal to 1. Yeah. So in other words, if you have your probability just now, if you add all of them, it will become 1. So to change the representation of the histogram from being a frequency or counts to probability, then you need to divide that with the total number of pixels. Yeah, total number of pixels. Example. Okay, let's look at example. Example. You have 4 pixels. Yeah. say that you have 0, 1, 1, 1. So if I tabulate that, okay. If I tabulate that, 0 appear 1 time, 1 appear 3 times, 2 appear 0, yeah, until 7 appear 0. This is for 3 bits. Can you all follow me? Yes? Do you understand how I get these numbers? 0 appear 1 time, 1 appear 3 times from this pixel. 2,
Yes.
we don't have any 2 here, so 2 appear 0 times, 3, 4, 5, 6, 7 appear 0 times. Do you all understand me?
Yes, Prof.
Okay.
Yes, Prof.
So for a normal histogram, 0, 1, 2, 3, 4, 5, 6, 7. For a normal histogram, we will plot 0 appear 1 time here and 1 appear 3 times. Yeah, 3 times. So this is a normal histogram. Okay. Now, if we want to use a normalized histogram, so you need to divide. Okay, you need to divide 1 over 4. Yeah, 0 appear 1 time. Yeah, and then we divide 1 over total number of pixels. Yeah, total number of pixels. So 1 over 4, which is equivalent to 0.25. And for value color 1, which is dark gray, appear 3 times. So 3 over 4, it is equivalent to 0.75. So you can plot a normalized, a normalized histogram, but now your plotting label, it becomes 0.25 and 0.75. Yeah. And as I mentioned, if you add this probability together, you get 1. Of course, this one becomes 0 over 4, 0 over 4, all 0. You add all probability together, you get 1. So normalized histogram, if you add all of these values, yeah, you will get 1. Yeah, in other words, yeah, if you want to rewrite that, if you sum all of the values of the probability function, you get 1. Any questions? Wow, very heavy tonight, all mathematics, but not that difficult, right?
I just wondering,
Okay.
seen in a lot of example of, okay, for example, in RGB image processing, a lot of example need to convert this RGB to grayscale image before proceed to the image processing, including this histogram equalization stuff. Actually, what is the purpose of doing that? Is that necessary to do that one? Why we cannot just straight away do the processing on our RGB image?
Okay. Your question just now is you have one image, RGB. Okay. Most of the processing that you have found out in the literature, they say that the first step is from RGB, you transform that to becomes grayscale. Right? Before you do some image enhancement or image restoration. Okay? Most of the literature, they say that from RGB, transform that to grayscale. So your question just now, why do we need to transform to grayscale? Okay? So my answer is number 1, for simplicity. Okay? For simplicity, because if you, for RGB, one image actually, it is in a form of vector. Yeah. So first you have red, vector, and then you have a green vector, and you have a blue vector. So if you want to process image enhancement and image, if you want to process image enhancement and image restoration, yeah, for RGB, meaning that you need to process that number one in vector form. Number two, if you still want to process that in scalar, then you need to process that 3 times. Because you need to process that individually for red, green, and blue. Yeah. So that is the reason why most literature, if the purpose of the image processing can be done in grayscale, they will first transform from RGB to grayscale for simplicity. Number two, they may also convert from RGB to grayscale, because if you convert that to grayscale, then you will use less processing power. Yeah, and it will also be faster. Okay, so that's the reason why normally if you can process the image in grayscale, they will first do the conversion from RGB to grayscale. Yeah, because of the simplicity, you only need to look at one layer as compared to 3 layers in RGB. We will discuss about RGB when we go into color image processing later. Yeah. For now, we will only concentrate in grayscale. Okay, understand?
Okay, doctor.
All right, so we'll go next to, where's the PowerPoint just now? Okay, this PowerPoint. Okay. All right, let's look at one example. Yeah, after this example, then we can finish our class tonight. We have a 5 by 4 picture. So meaning that total number of pixels and K is equivalent to 20. 5 multiplied by 4. Okay. And if you want to calculate this manually, you know that 0 appear 1, 2, 3 times, right? 1 appear 1, 2, 3, 4, 5 times. 2 appear 1, 2, 3, 4. 3 appear 2. 4 appear 1, 2. 5 appear 1, 2. 6 appear 2 times, and 7 appear 0 times. 8, 10, 14. Okay. So if you add all of, if you add total number of pixels, you get 20 pixels, which is equivalent to 20 pixels. So I'm right. Okay. So you can plot as counts. Yeah. So if you plot that as counts, meaning 0 3 times, 1 5 times, 2 4 times, 3 2 times, 4 2 times, 5 2 times, and 6 2 times, 7 0. Okay. Anybody understand this? Yes. Okay. So next, we want to transform these values to become a probability. So if you want to transform that to become probability, then 3 divided by 20. Yeah. So 3 divided by 20 is here. Yeah. Sorry, it's not here. This is after processing. Yeah. So you have 3 divided by 20, which is equivalent to 3 divided by 20, 0.15. Okay. 5 divided by 20, 0.25. Okay. 4 divided by 20, 0.2. 2 divided by 20, 0.1. Yeah. So you can have another normalized histogram. Yeah, normalized histogram. Yeah, if you use these particular values here from 0 up to maximum of 0.25. Sorry, 0.25. So that would be the same histogram as this one, except that it is now in normalized histogram. Yeah. So in histogram equalization, okay. Anyway, before I proceed, I just want to give a remark that this is there are many ways of doing histogram equalization. If you read books, if you read papers, they have different ways of doing histogram equalization. The whole idea is still the same, to try to spread out the values of the frequencies in histogram. Yeah. So the purpose is what I'm teaching you tonight is just one of the ways of histogram equalization. If you read papers, they might have different ways. Yeah, because this is an area of research. So meaning that if suddenly you think, oh, can I do this? Oh, can I try to plug in some other parameters and get better results? So you may do that and you may publish. Yeah. So this is an area of research. So now, coming back to the last equation, the way that we do histogram equalization here, first, number one, you get these values, yeah, which we already got there. Yeah, these values. Yeah. Okay, up to 0.1, 0.1, 0.1, and 0. We have these values already. Okay. But the way we do that is by totaling up the values up to that particular point. Yeah. So that's why earlier 0 appear 3 times. So I have 0. So 0.15 for value of 1 RK1, okay, 0.15 plus 0.25, okay, 0.15 here plus 0.25, okay, which you get 0.4 lah, right? 0.15 plus with 0.25. So for these two is actually 0.15 plus 0.25 plus 0.2. Yeah, plus 0.2, then you get 0.6. Yeah, so on and so forth, and eventually when you go into 6, this is actually 0.15 plus 0.25 plus 0.2 plus 0.1 plus 0.1 plus 0.1 plus 0.1, then you get 1. And for 7, even though that earlier 7 got 0, but because we are cumulatively including the previous normalized histogram values, then you get 1. So actually, if you want to plot this, this now becomes a cumulative density function graph. Okay. Next, in this method, we then multiply that with 7, yeah, because maximum value is 7, so it's actually 3 bits. So 0.15 multiplied by 7, 0.15 multiplied by 7, you get 1.05. Yeah, 1.05. I did mention in our first class or second class, values for colors, it cannot be in decimal. It has to be or must be in integer. So for 0.15, we take value of 1. In other words, any value that you get 0, it will be changed to 1. Okay. Next, 0.4 multiplied by 7, you get 2.8. So 2.8, the closest is 3. Yeah. So any value of 1, it will be changed to 3. And then next, 0.6 multiplied by 7, you get 4.2. So 4. So anything with 2, it becomes 4. So that's why here you get 1. The original value is actually 0. So 0, you use this technique of histogram equalization, you get 1. 1, yeah, 1. You use this technique of histogram equalization, it becomes 3. Okay, so on and so forth. And you can see also 7, because 1 multiplied by 7, you get 7. So if you have value of 7, it will change to 7, meaning no change. But since that this is 1, meaning this is 7 as well. So anything you get 6, it will become 7. So what this particular technique is trying to do is trying to equalize. Oh, okay, I shouldn't use the same color. Hold on. Okay, I don't know why I cannot erase. Let's just, okay. So what this particular algorithm is trying to do is trying to equalize the distribution of the histogram, yeah, as compared to the okay, why cannot change? Trying to, okay, oops, yeah, as compared to the original histogram here, yeah, this particular histogram after this method, you can see that now the values are being more distributed, yeah, and maybe it's quite difficult also to see because we have a limited number of pixels. But if you have a very huge number of pixels, massive size of image, then you'll be able to see a better redistribution of histogram values. Okay, so this particular technique is called as histogram equalization. And again, my disclaimer just now, this is just one of the available techniques in histogram equalization. There are lots of other techniques in histogram equalization. Okay, so we can further extend the okay, we can further extend the histogram equalization technique by introducing a transformation function in histogram equalization. Okay, so just now, okay, just now, why I cannot change the slides? Okay, just now, the way that I decide the new value of the histogram is just by multiplying with 7 bits. Yeah. Now, instead of relying on the cumulative density function, this one, instead of relying to this one, I can also introduce any types of transformation function. It could be like, it could be like this. It could be like this. It could be like this. I can introduce any transformation function. Yeah. So with this transformation function now, I can replace this value here, yeah, to be based on this transformation function. So meaning that I will not use this normalized value anymore. Yeah, I do not need that. Yeah, I just use this right away. For example, maybe this is 5 and 5. Okay, 3 equivalent to 5, for example. So I can use right. Oh, okay, sorry, accidentally I. Okay, so I can use right away. I can use right away the value of of this particular transformation function, and instead of using these values here, I will just use the value that I have in this transformation function. Yeah. So I give my example just now. This is 3, now becomes 5. So earlier we have 3 multiplied by 7. 0.7 multiplied by 7 got 4.9. So earlier, based on this algorithm, 3 will change to 5. Yeah. How I get 5? 0.7 multiplied by 7 is 4.9. The closest integer value is 5. But if I use this particular equation of transformation function, I just do the interpolation. From 3, I get 5. Yeah, so from 3, I get 5. Yeah, so this is called as histogram matching. Yeah? Histogram matching. Because now I combine the first technique of transformation function using the transformation operator with histogram equalization. Yeah, histogram equalization. Yeah, so I kind of like doing a hybrid of that two methods, and now it becomes a histogram matching. So the histogram will then after that match the cumulative density function of this introduced function, newly introduced function. So this particular function, again, I don't have answer which function is the best. I don't have that answer. It depends on what are the problems that you have in your image. Yeah? You can either use a simple image equalization, or you can then introduce a transformation function in your histogram. Yeah, remember this is histogram. Yeah. Last time when we discussed earlier about image enhancement transformation function, that is for the value of the pixels. But here it's not the value of the pixels, but the value of the histogram. Okay. Any questions? Because I'm done for tonight. Okay.
So, Prof,
Okay, continue.
for histogram matching, we can directly match from the original histogram, or it is compulsory to go first for the equalization and then go for the matching. Can we directly go for the matching from the original histogram?
Sorry, again, your question, can you go to matching? Sorry, again?
If first we have a histogram of the image, then we can directly match our histogram to the function like we here is dr and d, something like this function. Mean it's not compulsory to first go for the equalization and then go for the matching. We can directly use any function to for histogram matching.
For histogram matching, you can introduce any function, yes. But whether the function will work or not, it really depends on what are the problems that you are currently facing with your image.
This function should be always cumulatively increasing.
Sorry, are you referring to this particular function in this example? Because this is just an example.
Yeah, this one and also for the other example, or it can be in any shape. Maybe initially at the peak and then decreasing, maybe, or it's compulsory.
You can introduce any function,
okay,
but it depends on the problem of the image. Okay. I'm just providing you the platform here, because we are not going into detail into specific application. But if you, when people ask you about histogram equalization, you need to understand that histogram equalization means that you are trying to redistribute the histogram so that it will cover more areas, and in terms of the frequency, the intensity also, it will be more distributed, more fair. Yeah. So that is histogram equalization. As for histogram matching, you're trying to change the shape of the histogram by introducing one function.
Yes, indeed.
Yeah. Similar like when you do earlier in image enhancement, when you introduce a transformation operator, you are introducing one function also to try to assist you in your specific application. Yeah. But what function is the best? That really depends on you. What's your problem? If your problem is about it's too dark, then you need to increase the darker region. Yeah. So maybe your function would be something like this.
Yeah.
Yeah. Or if the image is too bright, then maybe it is something like this. Okay.
Right.
All right. Any other questions? Okay, so if not, then that's all for tonight. Thank you very much, everyone.
Thank you, Prof.
I hope that you have a good night's sleep after all the mathematical
Prof.
equations that we have tonight.
Yes.
Right?
Thank you, Prof.
Take care.
Thank you, Prof.
You can download the slides from Putra Plus, okay?
Thank you.
Okay, thank you, Prof.
Okay, bye everybody. Take care. Good night.
Bye.
Assalamualaikum.
Bye.
Bye, Prof.
Bye.